Alright, so 23 we'll start with, really basically, all you had to do with 23 was translate it into vectors that you're used to seeing, okay? Cosine of pi over 3 is what?
1/2 root 3 over 2.
It's 1/2, so 1/2 I plus, what's sine of pi over 3?
Root 3 over 2.
Root 3 over 2. J, okay? Or you could rewrite that as simply the vector 1/2 root 3 over 2. Oops. Root 3 over 2. Okay? So then we have 3 pi over 4. Cosine of 3 pi over 4 is
1/2. No, root.
if you're not focusing on what we're doing, you're missing out, and you're not gonna listen. You gotta focus here. Okay.
Negative root 2 over 2.
Negative root 2 over 2.
And then sine is root 2 over 2.
Sine is positive root 2 over 2. We're in the second quadrant here. So that's J. So root 2 over 2. Sorry, negative root 2 over 2, root 2 over 2. Okay, so now when I do the dot product, it's the same thing, I just have some fractions and radicals involved. Alright, for the dot product of u dot v, we're doing 1/2 times a negative root 2 over 2 plus root 3 over 2 times root 2 over 2. Okay, so it would be a negative root 2 over 4 plus root 6 over 4, which you could write then as root 6 minus root 2 all over 4. And that's as simple as you can get it without going to decimals. Okay.
Do we have a test next week?
Yeah, on Tuesday.
I like so many.
So, and the trimester stuff, so.
Next week's the last week.
Next week is the last week of the trimester, so. Alright, so any other questions from homework? Problems?
Is it a chapter test on Tuesday? Or a whole
Yes, it's only 4 sections, section 1 through 4, but they were pretty big sections. The law of sines, the law of cosines, the 2 area formulas, and then the stuff about
the
vectors.
whole
It's only 2
chapter
seconds.
6.
Yes.
4 seconds.
Now, there is a 5th section in chapter 6 that we're not covering on the test. We're going to really briefly cover it next Thursday and Friday. But it's not going to be on your chapter 6 test. Kind of making that a appendix to the chapter. Alright, Faith, any questions about this homework? Alright? Anything? Alright.
Are we gonna learn anything on Monday that's on the test, or is everything we learned up till today?
My plan is to finish everything today that
Okay.
will be covered, so. Alright, here we go. So, kind of a familiar diagram. I want to start with, we had a problem similar to this earlier. But I want to revisit this because your book actually covers a concept called projecting one vector onto another, and it finds components that way. Personally, I think that kind of overcomplicates things. We're going to end up doing a lot of the similar mathematics, but just keep it kind of in simpler terms. Alright, basically what we're doing is we're going to find components of vectors without using the projections like the book does. So let's look real quickly here at the diagram, the type of thing that we're going to look at. Our main force vector, if we're looking at this boat on a ramp, okay, the main force vector is going to be gravity pushing straight down. But then we want to consider the two components of that. We want to consider the component of how much weight the ramp itself is having to support, okay, and then how much force or how much weight is pushing it down the ramp. And that's this vector right here, okay? And just so you can see it a little better, that they're calling W1, the vector right there. This vector here is W2. And this vector here is our force vector. Okay? Now again, I want to define these in terms of the situation. The force vector going straight down is simply how much the boat weighs. How much the boat weighs. The W1 is how much force is pushing the boat down the ramp. Okay? And then lastly, this W2, the W2 is how much force the ramp has to hold. Okay? So that's what we're breaking this down into. And this is significant for a couple of different reasons, all right? If we're trying to pull the boat up the ramp, obviously we have to overcome W1, all right? So if this boat, the nice thing though is if this boat weighs 6,000 pounds, we don't have to be able to pull 6,000 pounds. We just have to be able to pull enough to overcome that W1. If we're building a ramp, probably be built out of concrete, but if it's not, alright, if we're building the ramp, it doesn't have to be able to withhold the full 6,000 pounds either. It just has to be strong enough to hold the component of that 6,000 pounds that is W2. Okay? Now, the way we're going to solve this, and this happens a lot, and whether we're dealing with this situation or we'll look at some others. Here we have another ramp problem. We're talking about work over here, and we'll be looking at things pulled at an angle, okay? But with all of these, we're going to be looking at certain angles, and we're going to make right triangles out of them. Okay? This W1 is going to be the same as this vector down here. Okay? That's W1. Okay, remember vectors are not tied to a certain position. So we're going to move it down here. And because we're talking about, because of how we defined these, we know that W1 and W2 are orthogonal. What does that mean again?
It's a right.
Yeah, they're at a right angle. They're perpendicular to each other, okay? So we know that this angle right here is a right angle. So guys, much of the trig involved here is just going to be right triangle trig. Now, there's also an element of this that involves some similar triangles, and let me show you how that works. Okay, and this is important to understand the angles. I'm going to actually copy this so I can write on it without messing up the original too much here. Okay. Let's look at how we figure out the angles. Okay. Now, usually the angle that we're going to know is going to be this one right here. Okay. We're going to know the angle that the ramp makes with the horizontal. Okay? So that's what we know. Watch this though, because this is going to be key to getting your angles correct. Okay? You with me here, CJ? Kenny? Yeah. Come on.
Yeah. You like jerked off.
Alright, now look. This force of gravity is going straight down. This is the horizontal. So I know this is a right angle right here, correct?
Yeah.
Correct.
Correct. Alright.
Okay.
Now, I also know that W2 is perpendicular to the ramp itself. So I know that's a right angle. Okay? Now look. This angle right here between the ramp and the force vector going straight down is going to be the complement of this angle right here. In other words, they're going to add up to 90 degrees. Okay? Now, I know that not only does this angle plus this angle add up to 90 degrees, but also because I have this right angle here, I know this angle, the one up here, plus this angle equals 90 degrees. So question, if this plus this is 90, and this plus this is 90, what do I know about these two?
They're the same.
They're the same. That's the key to getting your diagrams right. Okay? That's the key. Get a different color. Alright, so I know this angle is going to be the same measure as this angle here. Okay?
So it's the angle at the top of the triangle rather than. Okay.
Mm-hmm. And then also, remember we said W1 was parallel? It's the same vector as is up here on the ramp. So those are parallel. As a result, you guys remember alternate interior angles?
Yeah, you could have just used the
Okay. So this angle right here is going to be congruent to this angle right here. Okay? So that's again how you can get the angles, alright? So be careful, it's really easy. A real common mistake is that people will take the 30 and they'll put it down here. Or whatever this angle is and they'll stick it down here. Be careful that you get your angles in the right positions. Okay?
Mr. Nixon.
Yes.
What does congruent mean? I just forgot.
Equal measure.
Oh, okay.
Okay? Now that one I wanted to take a problem we had kind of worked through before a little bit, and I wanted to break down the diagram a little bit more because now I want to actually use this to solve a problem, okay? So here we have, we're going to find the components of force involved in the situation here. We have a cart that's sitting on this 30-degree angle road, okay, or ramp. And we need to figure out how much force is required to keep it from rolling down the ramp. How much force do we have to have in order to keep it from rolling down the ramp?
Can I borrow Lisa for Lola for
Okay. Alright, so let's look at what we're given. Let's label it in our diagram. And then figure out what we need to figure out. Okay? So it says a 200-pound cart sits on a ramp inclined at 30 degrees, as shown in the figure. What force is required to keep the cart from rolling down the ramp? Alright, so what are your initial thoughts here?
Other angles should be 60.
The other angle should be 60? Okay.
The one like we're above W1.
Okay. So this right here should be 60.
Yeah.
And then this down here would be 30. Okay. The force. Okay, the force is going straight down. Alright. And how much force is that? That's 200. Okay? Because it weighs 200 pounds and gravity pushes straight down. Alright? Now, here's the W1 they gave us. And this is where it's helpful. We're going to draw from where our force is perpendicular to the ramp. Okay? That's how much force the cart is actually exerting on the ramp itself.
Is it the same thing as the dotted line?
It's the same as the dotted line. Okay? It's the same as the dotted line, but
Don't we just need the not that force, but the other one that's going this way?
you're right. We're going to use the we're going to find that with our right triangle here, because this right here is the W1, which is how much force is pushing the ramp down, or pushing the cart down the ramp. Okay?
It's a 30, 60, 90 triangle.
Why do I need to find that?
And you just do like 30.
Hang on. Listen to the question. Why do I need to find W1?
30. That's the force
that's
going
the-
up to pull the car.
That's the force going of the ramp on down the cart.
Yeah.
Couldn't you just?
But what are we trying to find?
It's 100.
You're trying to find that W force that's going this
And
way.
you
Couldn't you just use the
Hang
right
on.
triangle you already have
Yeah.
there?
Just
The
do
30, 60, 90 triangle with 200 pushing down, and then just
200
solve
side.
for the leg right here.
You can. I was just drawing it the same way that
We drew the other one.
we drew the other one to relate the two.
So you can do
Okay.
200 sine 30.
Alright, so we have, but we still haven't answered the question. Why do I want to find W1?
That's the
W1
force.
is the force that's pushing it down the ramp.
So,
That's the amount of weight
we
that
wanna
the
know
ramp
how
is
much
This is
doing.
just a difference.
It's required to keep it from rolling down the ramp, so that's the amount of force you need to stop it.
Okay.
It's exerting.
if that's how much force is pushing it down the ramp, then if we want to keep it from going down the ramp, we've got to have the same amount of force pushing up the ramp. Okay? That's what we're getting towards here. And that's what they drew here, this vector V. That's the amount of force pushing against it to hold this thing still.
Wait, isn't the force, like, shouldn't it be 200 times gravity?
No, that is the weight.
Or the weight and then mg?
It's not, well, it's not mass, that is the weight.
Oh.
That's the force. If we had mass, it would be like in kilograms or something like that. Okay? So here, just again, to look at the triangle that we're using, we have this right triangle. This is our W1 that we're trying to find. Okay? We know this is 30. We know this is 60. We know that this is 200 pounds. Okay? So, a couple of you said 30, 60, 90 right triangle. And one said use sine
Yeah.
of 30. Okay?
Yeah.
So the sine of 30 degrees is going to be the magnitude of that W1.
Over 200.
Over 200.
Yeah. You could also use the pattern. If you remember the pattern for a 30, 60, 90, you could find it that way as well. Sine is a half, so if the magnitude of W1 over 200 equals a half, then
100.
it must be 100. Okay? Okay? So we need 100 pounds of force pushing up the ramp in order to keep it from rolling down the ramp. Okay?
So we just use a law sign, right?
No, we didn't.
No, we just used right triangle trig.
We use law
If you did use the love signs, it would work
sign.
too. It's just an extra step. Okay? Now, I personally like doing it this way. If you want to read the book and see what they're talking about with projections and all that, you're welcome to do that, but personally I like doing it this way better.
And there's never going to be a situation we hit where you have to use projection.
Yeah.
No, I mean, it may add a step, maybe, to the problem. And actually, like the ones we're going to look at here when we're talking about work, it will add one step to it. But I think adding one step that we already know how to do is better than trying to memorize a whole new process. That's my opinion.
Well,
So.
this is how we solve problems in physics all the time.
Yeah, and this is the more common way in a physics class that you would do it. Alright, so that's finding a force component. The next thing we want to talk about is work. Okay? Work is a basic concept for those of you who haven't had physics yet. The work done by a constant force F acting along a line of motion of an object is given by W equals the magnitude of the force times the distance. The magnitude of the force times the distance. Okay? Now, how do we measure force?
Newtons?
In either newtons or in
No.
pounds.
Nope, that's fine.
Okay? And
Suck at physics.
often we'll use pounds, but just out of habit I use pounds more than I use newtons. But then in distance, for distance, we'll often measure the distance in feet. Or if we're using metrics, we'll measure it in meters. Okay? So we're either multiplying here pounds times feet, or we're multiplying newtons times meters. Okay? And that's how we actually get our units of measure. Okay? Our units of measure for work are foot pounds, or Newton meters.
Don't we use joules for
remember what joules are. I think
Joules is an
joules are
energy unit.
Yeah.
power, yeah. Now, if you ever like work on a car or something like that, you might see in the directions when you're installing things that you need to use a certain number of foot-pounds of torque. So you get a torque wrench, and it'll show you, you know, you can set it to a certain number of foot-pounds, so you don't shear off the bolts or tighten it down too tight or whatever. But anyways, we have foot-pounds or newton meters. Okay, the constant force F is not, if the constant force F is not directed along the line of motion, the work done by the force is given by, and they have one formula that uses the projection, or we're going to look at this formula, the force times the distance. It's a dot product form, okay? So notice what we have here. We have force that is pulling directly in line with the way we're trying to go. Okay? That one's a little easier because they're going in the same direction. Alright, you don't have to do anything with the force. However, a lot of times we're pulling on something with a force that's not exactly in the same direction where we want to go. Think about pulling, if you have a little brother or sister, pulling them in a wagon. Okay? You grab the handle and you're holding the handle usually not at a perfect horizontal, or else you have to kind of walk like this the whole time. Alright? You're usually pulling it at an angle behind you. Okay? So some of your force is pulling them horizontally, but some of your force is actually lifting the front end up. Okay? That's why if you see little kids try to pull each other on scooters or whatever, a lot of times they'll just yank on it and they pull the front end up and the kid falls off the back, you know, because they have too much of their force vector going up than horizontal. But what you have to do in this case is find F in the component form, and really what we're looking for here is this horizontal component of that force vector. That's really the one that we're concerned with when we're talking about the work done. Okay? Now, the vertical component could be useful to make sure we don't flip them over, but the horizontal one is the one we're going to use in determining work. Okay? So, let's look at an example where we have this come up. Okay? And we're not talking about the projection, so I'm going to paint the barn here so you don't even see that. Okay. So here we have this door, and there's a rope attached to the top corner of this door, and it's a sliding door that slides across. Okay? So what we have to do is we have to determine both the horizontal force vector and the horizontal motion vector, or displacement vector. Okay? Now, let's read the whole problem and then we'll get into that. It says, to close a barn sliding door, a person pulls on a rope with a constant force of 50 pounds at a constant angle of 60 degrees, as shown in the picture. Find the work done in moving the door 12 feet to its closed position. Alright, so PQ is a displacement vector. Okay? Okay, that's a displacement vector. If I move it 12 feet to the right, then what's my vector?
0, 12. 12-0.
12-0. Okay?
I was close.
12-0. Okay? So that's easy enough. We've got now the number of feet that it was moved. Now we need the horizontal amount of force. Okay? So we're going to get, we're going to find the force vector in component form. Alright? How do we find, if we know the angle and we know the magnitude, how do we find the force vector, or the component vector?
Trig.
Some trig. Let's think about this. Our angle is 60 degrees right here, right? So what's the direction angle of that vector?
Direction angle like from 0?
Direction angle means direction angle. So it's always standard position.
120.
No?
No. It's 100.
300.
Oh.
Okay? 300. Now that's important because to use our formula that we had, we want F is going to equal the magnitude of F times cosine of the direction angle, sine of the direction angle. This is the part that maybe this is an extra step that you wouldn't have to do if you did projections, but now you don't have to do the projection. So I think it's kind of the same either way. And this is a little easier conceptually. So, let's think this through. What is the magnitude of the force we're dealing with?
50 pounds.
50 pounds, okay? 50 pounds. So 50 times, what's the cosine of 300? A half. Cosine of, it's a 60-degree reference angle in the fourth quadrant. So that's a half. What's the sine of 300?
Negative root 3 over 2.
Good, negative root 3 over 2. So now I know it's 25 and negative 25 root 3. Now, don't bother finding that as a decimal, but this is why over time the thing the door's hanging on is probably going to get weak, because every time you shut it, you're using 25 pounds of force to actually shut it, and the other 25 radical 3 pounds of force is pulling it straight down against what it's hanging on. Okay? This is why things wear out over time. Alright, so if we wanted to make it last longer, we wouldn't tie the rope to the top of the door, would we? We would put the handle right in the middle so we can pull perfectly horizontal. Alright? Anyways, that's for free. So now we can calculate the work being done. The work is our PQ dotted with our force, foot pounds. Okay? So PQ we said was 12-0. We're dotting that with 25, negative 25 root 3. And what do we get?
You get 12 times 25.
300.
300. plus 0, right?
Yeah. Right.
That's why I said don't bother finding that as a decimal, because it's gonna come out to 0 when we do the dot product. So, our work done is 300 foot-pounds. Okay? 300 foot-pounds of work.
That sounds so funny, foot-pounds.
Yeah.
Yeah,
I thought it was pounds.
pound feet.
I've never heard of pound feet, Jose.
What?
Pound feet, never heard of it.
That's Thor.
Never heard of it.
Yeah, that's.
Maybe it's just different parts of the world, they put it different.
Is that from Brazil?
Different grammatical structures or
that's fine.
something.
You learned.
Anyways. Does that make sense?
That's because they use metric system.
Yeah. Yeah.
Nobody uses.
Yeah.
Yeah.
Except for Americans.
Yeah, Americans are the only ones who use
Okay,
feet
yeah,
anyways.
Which I hate.
But they use it in Australia.
So,
Anyways.
anyways, everyone understand what's going on here.
Teachers didn't want to switch to metric.
The arithmetic, or the trig here,
The teachers didn't know.
all the math involved is actually pretty basic stuff. It's stuff that we've done quite a bit of over the last chapter and over the year, okay? But it's just getting the concept from the situation that can be a challenge, okay? So, but that's how we can find work, alright? Now, the time that we have left, I'm going to have you guys get started. I gave you some different word problems, okay?
But it's not.
A number of various word problems. Some have work, some are just different forces, okay? I want to have you guys try some of these, and I want you to start now. On Monday, we're going to take time to review, tie everything together from the chapter, and then we'll have our test on Tuesday, okay?
I'll show you.
So, yeah, that would be good. Yes.
Well,